Can a sequence have a limit? If we are given some sequence named A and make n sufficiently large, will the sequence get very close to some limit, say L? Well, let's look at an example. Suppose A is defined like this, n plus 1 divided by n squared. Let's evaluate the limit of this sequence by making a table of values, graphing, and using algebraic techniques. So please, if you have access, open up GeoGebra. It is free online, or you can download the app. You will see me using the app version on my iPad. So when you first open up GeoGebra, you have some options. I selected Spreadsheet, and it shows me a graph here. So first, I'm going to enter some numbers. So I went ahead and entered the numbers 1 through 40. So what am I going to do with that information? So let's go to the top, and then I'm going to type in the equal sign. And if you recall, our sequence is defined by n plus 1 divided by n squared. So the column A, row 1, has n equals 1. So that's the first term. Column A, row 2, has the number 2 in it, which is the second term. So our n is actually represented by the column A and then whatever number we are at. So we're going to type in parentheses A1 plus 1, and then divide that by A1 squared. And we get 2. Now we can highlight this with our finger, and then rather than typing in the same formula 40 times, tap that little box or drag it with your cursor down until you get to 40, and it filled in the values for you. So here you've just created your table of values, and you can use your cursor to scroll down and notice that this sequence is getting smaller and smaller and smaller as n, and n is here in this first column, gets larger. So at first glance, I think this is tending towards 0, but let's double check by doing our second representation of the sequence. That is by using a graph. So I'm going to go ahead and highlight the first 2 columns using my arrow keys. And then if you notice up at the top, there is a button with a bracket, 1, 2 bracket. Click on that. And go list of points is what you want to select, and you're just going to say create. And that's really lovely what GeoGebra has done, since now we can go to move graphics view and we can really see, let me not do that, there we go. We can really see that this is definitely tending to get closer and closer to 0. So now we have both a graph of our sequence and a table of values. Finally, let's use algebraic methods. So on your own notes, you can print out the GeoGebra table, copy it down, print it out separately, but on here we're just going to use the algebraic methods. So how about we try the limit as n approaches infinity of n plus 1 over n squared. And this is a fairly straightforward limit that you should remember from the first semester of calculus. And this just becomes the limit as n approaches infinity of 1 over n plus 1 over n squared. And each of these individually, as the denominator gets larger, they're going to tend towards 0. So this limit is 0. So it looks like our table of values, our graph, and our algebraic methods are all leading us to the conclusion that maybe the sequence does have some limit, but now we need to define that. So let's take a moment and define what we mean by a limit of a sequence mathematically. Definition: the limit of a sequence. A sequence A has a limit L if we can make our sequence as close to L as we like by taking n sufficiently large. If the limit of a sub n equals L, we say a sub n converges, and we write the limit as n approaches infinity of a sub n equals L, or our sequence A approaches L as n approaches infinity. Otherwise, we say the sequence diverges. Note, the limit laws for sequences are similar to the limit laws from the first semester of calculus. I've printed them below as for reference only, but I will not be going over them. So these limit laws are on your printed notes. Please take a moment to review them independently. Next, some theorems. If the limit of this function as x approaches infinity equals L, and our sequence A can be defined by this function evaluated at n, where n is an integer greater than or equal to 1, then the limit as n approaches infinity of the sequence is equal to the limit of this function, that is L. Next, we have the squeeze theorem, and this is also very similar to what you remember from Calc 1, so from the previous semester of calculus. Given these sequences A, B, and C, suppose there exists some integer big N, so that for all little n greater than or equal to big N, we have the following inequality. If there exists some real number L, such that the limit of the outer sequences is equal to L, then this sequence converges, and the limit of the sequence as n approaches infinity is equal to L.